Remember what a rational number is? A rational number, no one? A number is rational if it can be written as a fraction of two integers. It's what we used to think of fraction. A number is rational if it can be written as a quotient of two integers. Now, square root of 2 is the one irrational number we dealt with, but there are lots of them. For example, square root of 2 is too big. It doesn't fall between 0 and 1, right? Square root of 2 is our first irrational number, but if you divide it by 2, it's still going to be irrational, and now it's between 0 and 1. Display will never land on this point, because you cannot write this point as a fraction of two integers. So if you, like I did back in high school, think that, yes, display will land on every point, then you still think that the rational numbers fill up the number line. Not only that's not the case, actually display will miss more points than it hits. There are more irrational numbers than rational ones, which is crazy. So it will never land on any irrational number. What's an irrational number? It's a tricky one. It's one that you cannot write as a function of, as a quotient of two integers. That's a really bad property. And not only these numbers exist, there is actually more of them. Let me give you two important facts. If A is less than B, then the open interval AB contains a rational number. And here is another fact. If A is less than B, then the open interval AB contains an irrational number as well. You cannot take an interval so small that it doesn't have at least one of them. Every interval, no matter how tiny, will have a rational and an irrational number in it. So in that sense, they're both called dense, actually. They're both dense. Then AB contains an irrational number. But in a sense, there is much more irrational numbers than rationals. There are more. So there's a lot of them everywhere. There are more irrational numbers. And we're going to talk about what does it mean more with an infinite set. There are more irrational numbers than rational ones. So display will miss more number than it hits. How crazy is it? We're comparing three infinite sets, basically. One infinite set is all the points between 0 and 1. And another infinite set is all the rational numbers between 0 and 1. And the third one is all the irrational numbers between 0 and 1. And as it turns out, the irrational numbers, there is more than the rational ones. So that was kind of a surprise to me way back. Okay. So my math teacher used to say that if you throw a rock at the number line and you hit a rational number, that's cause for celebration, because your chances are you're going to hit an irrational number. Okay, so we were looking at decimals. And we agreed that terminating decimals always represent rational numbers. So for example, 12.30203 is rational because we can grow a 1 and then 1, 2, 3, 4, 5 zeros after the 1. We multiply upstairs and downstairs by that. We're going to get an integer over an integer. 30203 over 1. And then we multiply both upstairs and downstairs by 10 to the 5th power. We get 1,230,203 divided by 100,000. Integer, right? So terminating decimals, always, you can always rewrite it as a fraction. That's one way. Any questions about this? And then I made a mistake. I said, okay, so what we proved is here are the rational numbers. And here are terminating decimals. And we have established that if a decimal is terminating, then the number it represents is rational. But that's not true backwards, because just think 1/3. 1/3 as a decimal is 0.3333. There is notation for that. And then I made a mistake of, I started to divide 1 divided by 23. And I hope that it would 11-digit repeating block, but actually it has 22-digit repeating block, and we ran out of time. So let's be a little bit more modest and let's look at 7. 1/7. If you look at it with the calculator, I don't know if it's clear to you, if it's terminating or repeating. It's just, who knows? Who knows, right? So that's why sometimes we are smarter with the paper than with the calculator. So we're going to say 1, and we're going to divide it by 0. We're going to divide it by 7. Sorry. So 7 goes into 1. No, it doesn't. So 1 divided by 7 is 0. Multiply back, subtract. And then we bring down the next decimal. They're all going to be zeros that we bring down. But because we crossed the decimal point, we're just going to put it there. 10. How many times does 7 go into 10?
1.
1 times 7 is 7. We multiply back, we subtract, we have 3. That's the remainder, right? We bring down the next 0. 30 divided by 7. How many times can 7 go into 30?
4.
4, because 4 times 7 is 28. So we have 2, bring down the 0, 20. 7 goes into 20, how many times?
2.
2, because 2 times 7 is 14. 6. We did bring down the 0, 60. How many times does 7 go into 60?
8.
Yes, 8 times 7 is 56. We subtract, we get 4 for remainder. And then we bring down the 0, 40 divided by 7. How many times does 7 go into 40? 5. 7 times 5 is 35. We subtract, we get 5. We bring down the 0, 50. How many times does 7 go into 50?
7.
7, because 7 times 7 is 49. We subtract, we get 1. We bring down the 0, 10. How many times does 7 go into 10? 1. Just 1 times, right? 1 times 7 is 7. We subtract, we have 3. Bring down the 0, 30. I usually do this until my class stops me. Why could we stop here? 4 times 7 is 28. We subtract, we get 2, bring down the 0. 20 divided by 7 is 2. You see, stuff started to repeat, 142, 142. Here is when sort of the trap clicked and kind of locked us down, when we got a 1 again. See? Look, We're only bringing down 0. So the whole thing is predetermined. We're gonna have a 0 and a quotient of 1, 7, we subtract. So this thing is gonna keep happening over and over again. This is one loop that's just gonna keep happening. You see, it's sort of predetermined. So 1/7 as a decimal is a repeating decimal, but it's a pretty weird one, 6-digit long. It's actually, this is an orbit. The different remainders that you get is an orbit. And in case of a repeating decimal, that orbit has to do with, it has to be a divisor of the number that you get when you subtract 1. Because you're never going to get 0 remainders. 0 is a remainder, never going to pop up. But all the other remainders will pop up, or half of them, or 1/3 of them. That's why if you subtract 1 from 23, 22, I hope that it would be an 11-digit repeating block, but actually it turned out to be a 22-digit long repeating block. Here, when we divide it by 7, we're going to get a 6 digits long repeating block. 0.142857, 1428, so it looks like this. That's pretty bad. And so here is the first reason. Well, already in 1/3 was a reason why walk away from the decimals and use fractions. Fractions are friendlier. You're not going to be able to precisely enter this into your calculator. 1/3, yes. So decimals are sloppy in computation. You lose precision, or it's a terrible lot amount of entering. So this is the first argument for fractions as opposed to decimals. So what I want to show you now is that every repeating, well, if I just give you this 0.142857, 142857, no one would, well, I wouldn't know that it's 1/7. So what I want to teach you now is how to convert a repeating decimal into a fraction of 2 integers to prove that it's rational. So how to convert a repeating decimal to a fraction of integers. Therefore, to prove that it's a rational number. So every repeating decimal is also rational. To prove that it is rational. All right. Okay, so let's start with something simple. Oh, I call this the chop chop game. Chop chop. Okay. So let's start with 0.7777. I didn't want to use 0.33333 because that is probably recognizable as 1/3. But this one is not as recognizable, is it? And so the first step we're going to do is we're going to drop the bar notation, and we're going to write this dot, dot, dot notation. And I'm going to call this number x. This is a really strange equation. But I would like to point out that the dot, dot, dot is important because visually we see 4 times the digit 7, but how many times do we mean it? How many are we trying to represent here? How many times the digit 7 appears in this number? Infinitely many times, right? This dot, dot, dot means, now don't stop. So what we're going to do is we're going to use the badness of this number against itself. It's like when you drink alcohol for a hangover, sort of the cure is what the ailment was. But we're going to have to do a little trickery first. So what we're going to do is we're going to multiply both sides of this strange equation by 10. And I'm going to write the new equation above the previous one. So we're going to multiply by 10. 10 times x is 10x. And what do we get when we multiply this number by 10?
7.
7.7777. Now, without the dot, 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 this is a false statement. Because without the dot, 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 you had 4 times and now 5 times. That can be, but with infinitely many. Imagine that you have infinitely many pairs of couples lined up like this. Infinitely many men, that's kind of a strange, and infinitely many women like this. And then you take out one of the guys, and you tell these people to step one to the front. So this will go here, this will go here, this will go here, this will go here. Is there anyone who is going to be without a pair? And by a pair, I mean, no, everyone will get a pair. So it's kind of weird. You can remove one from infinity and it's still the same infinity. Or add one, something like that. So now we're going to use the numbers badness against itself, and we're going to subtract the second line from the first line. First of all, 10x minus 1x is just 9x. And what do we get when we subtract these decimals? 7. And now just look at this equation and solve for x. So we're going to divide both sides by 9, and x is 7 over 9. Now, I definitely want you to check with the calculator, and I intentionally worked with 7 and not something like 2, because I want you to notice the last digit. Did we get the answer wrong? Because the last digit is not the 7 there. Exactly. No, we didn't get the answer wrong. It's just 77 was rounded up to 80 at some point. If I do something like 2 over 9, then 22 gets rounded down to 20, but that you don't see, right? But what about 8 over 9? See, there is a little rounding there, rounding up. But we're right. The answer is correct. So this is why I call it a chop game, because the first goal is to chop off the infinite tail. Chop. You just want to chop off that infinite tail. All right. Any questions? Let's look at something more complicated. Something like, well, let's make it really bad. 2.538383838. Okay. Oops, I should have left a little more space. So let me tell you something. Multiplying this thing by 10 is not going to help, because if you move the decimal, and remember, we're going to do a subtraction next, so make sure that you actually align it. Don't just fake it, but align the decimals, because I see a lot of error coming just from don't just fake it, align the decimals. So when we multiply this thing by 10, then basically every digit gets promoted to a higher. 2 will become 20. 5 tenths will become 5 ones. That is the decimal. And then see what the issue is. That subtraction is not gonna remove the infinitely long tail. It will just switch to something else, right? But we'll get rid of the infinite tail if there is a if there is an 8 over an 8 and a 3 over a 3. So what number should we use instead of 10? We should multiply both sides by, well,
8.
No, 8 will not. So we're moving the decimal. 8 would completely change the nature of the. So we're using 10 powers basically
Okay.
But it's, so you want a 3 against a 3 again, right? So you have to move how much? In a real way. Use 100, right? If you use 100, then because this repeating block has 2 digits, right? 38, 38, 38. So if you take this 8, you want to promote it by 2 digits, not 1. And then you can think it's mysteriously, it just always works. So copy the decimal. So align the decimal point and then mentally move the decimal with your finger and then copy the number around it, but watch the alignment. So we're going to have 253. The 3 goes here, 253. And then the first thing is an 8, right? After the 3, there is an 8, and then a 3, and an 8, and a 3. That will work when we subtract, right? Not then 100x. So what do we get? Okay, so we're going to subtract the second line from the first line. 100x minus one of them is 99 of them. And now what do we get when we subtract this, these two decimals? So you can use the calculator, but you have to basically, if you want to use your calculator, again, I cannot overemphasize the alignment is important. 0, 0, 0, 0, 0, 0. Oops, this is what you want to perform with your calculator. Basically 253.8 minus 2.5. And we're not going to get an integer, but that's okay. The big enemy is the infinite tail. A finite little terminating, that's a very easy fix. So basically, there it is. 200. We're gonna get. I should be able to do it without the calculator. Okay, now you can do it either now or before it. But remember, the whole shtick is we want to prove that this strange decimal is a rational number. That means we want to rewrite it as an integer over an integer. 99 is an integer, but not this number. But there is a very easy fix. Just again, we're going to reach to a 10 power to move the decimal to the end. Basically, just a 10 will fix it, right? If we multiply both sides by 10, we're going to have 990x, and this decimal will walk to the end of the number. So we're going to get 2,513, 2,513. And now integer. So x, our number is quotient of two integers. We should definitely check. Now, one thing I want to say is that it is important to understand that we just want to prove that this number is rational. That means once you produce two integers, you don't have to worry about simplifying it. We could write it as an integer over integer. Job done. We prove that it's rational. We do not have to present it in its best way. So 2.538383838. So here I guess an 83 was rounded down to 80. It could have been that 38 would have been rounded up to 40, but that didn't happen. So half the time you will see that strange one digit at the end caused by the rounding. Any questions? So we multiply, let me just write this down. We multiply both sides by a 10 power twice. But what 10 power do we use? If we have something like 0.31262626, what do you think we need to multiply this number by?
1,000.
By 1,000. I'll show you one with 1,000. If you have something like 17.147.147.147. Don't worry about the beginning. Just look at the infinitely repeating block. And the length of that block is how many digits you need to move. So here you want to promote the 7, so it will stand above a 7. So it will have to go 1, 2, 3 places to the left, to the right. And therefore you need to multiply it by 1,000. If you need to rewrite this is 17.147. Right? 147, 147, 147. So we're going to use 1,000. Now here, the repeating block itself, which as you see, it doesn't have to kick in all at once. It's just 2 digits long, right? So don't worry at the beginning. Just think about it from the point of view of if you're a 6 here, after the multiplication, you should be standing above a 6. So it's 1, 2 digits. Basically, you just have to count how many digits long is my repeating block, because you want to shift it by a full block. So we use 100 here. I want you to try to do this one. Prove that this is a rational number. I'll give you a minute or two. Just do the same thing as what we did with the 7. Prove that this number is rational. Convert it into a fraction of 2 integers. And be prepared to be shocked. Yes, it does. This number, actually, if you open the door to infinity, strange things will crawl through the door. If you allow infinitely long sum, which is what an infinitely long decimal, these two are actually equal. Actually equal, not close. They are equal to each other. So here is the shocker. The decimal presentation of real numbers is not even unique. This number has at least 2 different decimal presentation. And you might worry like, oh, there is a third one. Actually, there isn't. So let me write it down. The decimal presentation of real numbers is not unique. Well, terminating decimals. For example, 0.24, you can catch up by saying, how about 0.23 and then 99999, but that's pretty much it. So this number has no third form. But even that should be a little bit of a shock, right? The computation, you should get 9/9 as it sits. Oh, so the computation would be 0.999 is x. We multiply both sides by 10. So 10x is 9.999. And then when we subtract, we get 9 here, 9x there. So x is 1. That's a little strange at first, but infinity does strange things. All right. So, but going back is that the first time, before you do the subtraction to chop off the infinite tail, you use the 10 power, and how many zeros should match how many digits in your repeating block. Don't worry about at the beginning. Don't worry about the beginning. Just find in there where it's safely, you can see that the repeating block is 2 digits long. Here, the repeating block is 3 digits long. And by the way, it could be perceived as 147 or 471, 147. So even this notation may not be quite unique. Does it make sense? If you have an 11-digit long repeating block, you're going to use 11 zeros after the 1, 10 to the 11. Let's do one with 4, okay? So let's say we have 102.38012701270127. You do not have to worry about the beginning. It is the infinite tail that matters. So it might take a while for you to realize, okay, it looks like that the repeating block is 4 digits long, right? That means that this 7 should be promoted by not 1, not 2, not 3, but by 4 digits, so the subtraction would work. So that means we're going to multiply both sides by, you don't have to know what number is, but 4 zeros after the 1. For 4 decimals, 4 zeros. That's 10,000. And then we get, and now you have to be very, very careful. This is one place where if you're one of those Eastern Europeans who uses graph paper, that might be in your favor. Because you don't want to fake this. You actually want to use the alignment. So we're gonna move the decimal to the right by 4 decimal places. 1, 2, 3, 4. So this number, and I'm gonna go backwards. So above the 2 comes this 1, then a 0, then 8, then 3, then 2, then 0, then 1. Let's see. This is 100. This is 100 times 10,000. Yeah, it looks all right. And then, so we were here 1, 2, 3, 4, and then it comes to 270, 127. I used to think this is so magical that it just works. because I used to think it from the point of view of the beginning of the number. But just think of one isolated digit, and you know that four decimal places will give you the alignment that allows you to chop off that infinite tail, right? So we're going to subtract. Now, if you want to use, well, whether you use the paper or the calculator, you want to find where it first is non-trivial, and that's right here, right? Right here. So here is where we start subtracting. 17 minus 8 is 9. 12 minus 4 is 8. Wow, this is a sucky one. I think we get a 0 here. Nope, it's even worse. Jesus. It's another 8. Wow, I couldn't have picked a harder one if I tried. I'm definitely going to check this with the calculator. So I cannot do this in English because you guys, I think, do it differently. 9. Oof. All right. And that would be 10,000 minus 1 is 9,999x. Okay. So let's just check it with the calculator. Now you don't have to worry about the alignment. You just have to worry about entering the number correctly. 1, 0, 2, 3, 8, 0, 1.27 minus 1, 0, 2, 3, 6. Oh, I'm sorry. Messed it up, didn't I? Okay, I started to subtract this. So 1, 0, 2, 3, 8, 0, 1.27, 1, 0, 2. I didn't do the 6. Oh, 1, 0, 2, 3, 8, 1.27 minus 102.38. Yep, we got it right. Okay. So that's the first multiplication. The second multiplication is to fix the terminating decimal. Don't worry about the short, finite terminating decimals. It's the infinitely repeating block, that tail that has to be chopped off. This one is an easy fix. What 10 power are we going to multiply two sides?
100.
But how much?
100.
100, right? You just want to walk this decimal to the end of the number. And you can divide by 999 and then multiply upstairs and downstairs by 100, but I prefer to do it right here. So it's 1, 0, 2, 3, 6, 9, 8, 8, 9 divided by 999,900x. So you see, no, you shouldn't have to simplify that. That's not the point here. But I'm going to be interested to see if we got it right. 889 divided by, did I get this right? Yeah, 10,000. Yeah, so 4 9s and 2 zeros. So 1 0 2 3 6 9 8 8 9. 1 0 2 3 6 9 8 9 divided by 4 9s and 2 zeros. Ta-da. See, it's so long, we cannot even really see what's going on. 102. Where is the original number? This is the original number. 102.380127. I wonder if we can climb to the end of the number. No. Well, one thing we can do, see, it's, maybe we can multiply it by 10 to see the next digit. Zero, 1, 2, 7. So I'm multiplying it by 10 powers, but I don't think we see more. It's just the decimal point is moving. So actually the calculator is too dumb to really help out. But from the beginning, it looks like we got it right. Okay, so I just wanted to point out the two multiplications with 10 powers. One of them is how long is your repeating block? And the second time, to fix the terminating decimal. All right. Any questions? All right, let's do just one. Let's say 308. Prove me that this is a rational number by converting it to a fraction of two integers. Hold on, this is too nasty, even for me. Let's do this one. This is a little bit more benign. Actually, it wasn't. Chop, chop. Let me know what kind of a rational number is this. See, I forgot to solve it myself, so I have an answer in my secret chat box. 8, 1. No. Or no, I didn't enter what you said. Well, at least one person has results. That's something. You know what? My one button is sticky. It doesn't have to push it down harder. 8122 over. You know, I just got something like 8.20222222. Oh, there it is. Okay, 8122. That's all right. At least you're trying. All right. We don't have time for me to wait for you to pretend to do this. I have no idea what you're doing over there. So the repeating block is 2 digits long. We're gonna have to promote this 3 to stand there. So we're gonna multiply both sides by 100. So it's gonna look 820.232323, 820.232323. Yeah, it works. And then we're gonna subtract 99x on the right-hand side. Gone, gone, gone. Wow, this one was much easier to subtract, wasn't it? Wasn't full of those terrible carrying and borrowing. This is 812.03. And then we're going to multiply both sides by 100 again, this time because to fix the terminating decimal. 81203. So we think that x is 81203 divided by 9900. You should always check with the calculator. You have no excuse to turning in a wrong answer. 81203. Make it maybe shaky hand. Divided by 9900. Ta-da. 8.2023. All right. Any questions?